Hello, dear ladies and gentlemen, dear colleagues. I'm glad to present to your attention a paper with the following subject: investigation of effects of microalloying elements and hot rolling parameters on the strength of low carbon steels. High strength low alloyed steels are widely used in the manufacture of vehicles, pipelines, buildings, engineering structures, and other objects for various purposes. This is due to a good combination of service properties, strength, plasticity, formability, fatigue, and corrosion resistance, as well as technological properties. The unique set of properties of these steels is ensured by the formation of finely dispersed homogeneous ferrite structure and a system of nanosized phase precipitates containing microalloying elements. Manufacturers of modern automotive sheet steels service to use the most cost-effective alloying variants. Therefore, relevant studies are currently being actively conducted. A special focus is given to searches for patterns of influence of chemical composition and parameters of hot rolling of metal on the formation of microstructure and system of nanosized phase precipitates of different types and ultimately the obtained mechanical properties. This work is one of the such studies. Low-carbon steels with the different combination of microalloying elements from the general titanium, niobium, niobium, vanadium, molybdenum system produced under the laboratory conditions were studied. The steels were smelted in vacuum induction furnace with a magnetized crucible. The chemical composition of the investigated steels is presented in the table. The steel ingots of all compositions were heated to 1250 degrees centigrade and rolled on the reservable rolling mill into strips of 12 millimeters thick with a rolling and temperature of 830 till 880 degrees centigrade. After the rolling end, the strip was cooled in an airstream with a cooling rate of 6 till 10 degrees centigrade per second to 550 until 590 degrees centigrade. When the strip was placed in a furnace heated to this temperature, kept for 60 minutes, followed the cooling with the furnace simulating the cooling of a roll. Mechanical properties. This slide shows the results of mechanical properties determination. As can be seen, the strange characteristic of the rolling simples vary over a wide range. The strange characteristics for titanium molybdenum microalloying system steels are higher, and the maximum values were obtained for titanium molybdenum 1 steel with a minimum carbon content, maximum molybdenum content, and the end temperature of hot rolling and winding 860 and 570 degree centigrade respectively. At the same time as the highest range values for the steels of this microalloying system, higher elongation values were obtained. To clarify the noted features of the behavior of mechanical properties, a study was carried out of structural state characteristics and the present phase precipitates in rolling steels. By means of scanning electronic microscopy, it was found that all study samples have a close ferrite microstructure. All samples of steels microalloying with titanium and molybdenum have a ferritic microstructure, while samples of rolled steels of the vanadium and molybdenum and niobium vanadium molybdenum microalloying systems have a ferrite perlite structure. Apparently, due to ferritic microstructure, rolled titanium molybdenum steels were more ductile. In titanium molybdenum microalloying systems, the ferritic matrix is basically two components and consists of ferrites of two morphological types, block CF and polygonal PF, with the exception of the steel of vanadium molybdenum microalloying system. In steel samples containing titanium and molybdenum, the proportion of polygonal ferrite prevails, figure A, and with a low carbon content, it's higher up to 17%. The grain size ranges from units of micrometers to average 10 microns. Individual grains exceed 2 microns. The shape of the blocks in the CF varies from approximately exhausted, figure B, to moderately elongated, figure C. In samples with a higher carbon content, quasi-polygonal ferrite is present in the microstructure, figure D, with approximately equates blocks with size of which is close to the size of PF grains. It was found that the density is of dislocation in polygonal ferrite and quasi-polygonal ferrite is low, and their distribution is chaotic, figure A. The density of dislocation in the block ferrite is high, figure B. In the rolled system samples of the niobium vanadium molybdenum microalloying system, the proportions of block and polygonal ferrite are comparable. Compared with the rolled steel samples microalloyed with titanium and molybdenum, the degree of elongation of the blocks is generally higher. The PF grain size also ranges from units of micrometers to average 10 microns. The density of dislocation in PF is slightly higher, from low to moderate. In vanadium molybdenum microalloying system, the ferritic matrix of rolled steel samples of the vanadium molybdenum microalloying steels consist entirely of PF, figure A. The typical grain size is the same as in the other samples. The density of dislocations varies from low to moderate. Cementite is present in all the samples studied except the rolled products with a low carbon content. In most rolled, the steel samples submicron carbonitride precipitates of about 0.1 till 0.5 microns in size are around in small amounts, figure A, in the steel of the niobium, vanadium, molybdenum microalloying system and cooled after the highest end temperature of hot rolling is 880 degrees centigrade, a large number of precipitates up to 0.2 microns in size were observed. Figure B. In the rolled steel of the vanadium molybdenum microalloying system are observed secretions were small, less than 20 till 30 nanometers. This is due to the low temperature as which in the thermodynamic conditions of the release of vanadium carbon nitrides occurs compared to niobium carbonitrides. The carbide and carbonitride precipitates form at an early stage of thermal deformation. Treatment in niobium microalloy steel increased to a greater extent, which was additionally facilitated by the higher end temperature of hot rolling. This slide shows the results of a thermodynamic calculation performed for vanadium molybdenum and titanium molybdenum microalloying system steels with minimum and maximum strength values, respectively. It can be seen that the total content mass percentage of the phase of VC and titanium CN are approximately the same. However, due to kinetic feature of the separation process, which depends on the presence of molybdenum in the steel, vanadium carbide is released with a significantly low molybdenum content, approximately 0.20 weight%, are larger and their number is smaller. Analysis of the results of the study of steel microalloy with the titanium and molybdenum shows that steel with a low carbon content and higher strength was distinguished not only by a high concentration of molybdenum in the production of hot rolled products from its higher temperatures of the end of rolling and winding were used 870 degrees centigrade and 580 degrees centigrade respectively. This investigation of microstructure characteristics, phase separations, and mechanical properties of low-carbon hot-rolled steels of various microalloy system and containing molybdenum in the amount of 0.12 till 0.24 weight% allowed us to establish the following patterns. When cooled at a rate less than 10 degrees centigrade per second after steel rolling is completed, titanium molybdenum microalloying system have a ferritic microstructure. Vanadium and molybdenum and niobium vanadium molybdenum are ferrite perlites. In this case, the ferritic matrix is two-component. It consists of polygonal and block ferrite characterized by low and high dislocation densities, respectively. At a relatively low concentration of manganese, average 1%, hot rolled products of titanium molybdenum microalloying system demonstrated high tensile strange values of 730 megapascals, which correlate with the observed large number of nanoscale phase precipitates. At the same time, due to the single-phase ferritic microstructure, the maximum elongation values were obtained up to 31%. The results of the study shows the implementation of the interfacial separation mechanisms contributed most effectively to achieve a high level of strength due to the contribution of dissipation hardening. Favorable conditions for this are the temperatures of the end of rolling until 880 degrees centigrade and winding till 590 degrees centigrade. The use of molybdenum alone leads to the formation of smaller nanoscale complex carbides, but to ensure a large amount of them, the concentration of molybdenum must be at least 0.16 weight percents. Thank you for your attention.